An ellipse that has a horizontal major axis will have an equation x squared over a squared plus y squared over b squared is equal to 1. Or, if it has been translated, x minus h the quantity squared over a squared plus y minus k the quantity squared over b squared is equal to 1. An ellipse with a vertical major axis is going to look like x squared over b squared plus y squared over a squared is equal to 1. And if it's translated, it's going to look like x minus h the quantity squared over b squared plus y minus k the quantity squared over a squared is equal to 1. Note that a is bigger than b for all of these scenarios. Also, in all cases, the foci are given by the equation a squared is equal to b squared plus c squared. Now, not only do ellipses have different orientations, ellipses have different roundnesses, we can say. Some ellipses are more elongated, and some ellipses are more circular. And this is true irrespective of their orientation, right? They can be sideways, they can be vertical, they can be more elongated, they could be more circular. The more elongated an ellipse is, the farther from the center or relatively closer to the vertices the foci are. The more circular an ellipse is, the closer to the center the foci are. Using the convention that the distance of half of the major axis is a, and the distance between the center and a focus is c, we can talk about how elongated or how circular an ellipse is using an idea of eccentricity. Eccentricity E, not Euler's number E, just eccentricity for an ellipse, E, is the ratio c over a. And because c is less than a and c and a are both positive numbers, the ratio c over a is always between 0 and 1. And we can see from this very elongated ellipse that c is fairly close to a, and so its eccentricity is close to 1. And so an ellipse whose eccentricity is close to 1 is a more elongated ellipse. An ellipse where the foci are close to the center is going to have a relatively smaller numerator. And so closer to 0, we have ellipses that are more circular. We often see eccentricity discussed in the context of planetary orbits. Johannes Kepler discovered that planets orbit their sun in an elliptical orbit. And here's a picture of our solar system with our bunch of our planets there circling around. And those orbits look mostly circular. Pluto looks a bit off. It's a little more elliptical. But we see here the path of Halley's Comet, and it is clearly much more elliptical. So we would say that the eccentricity of Halley's Comet is close to 1, whereas the eccentricity of our Earth's orbit is close to 0. I don't know how close to 1 and close to 0 mean, but we can clearly see Halley's Comet more elongated. And then here we have another image that has various orbits. The blue one that looks like a circle is Jupiter. This orange one that's coming kind of out of the picture there, that's Halley's Comet. And then we can see there are several other comets there. I don't know which ones they are. You could Google this picture. I just Googled planetary or comet orbits. But you can see that they are in varying degrees of eccentricity, but they're all elliptical. What's more, the sun is at one focus for all of these elliptical orbits. Well, I think I would be remiss if I didn't show this picture of a cone being sliced. We saw in a previous video that if we slice using a plane that is parallel to one edge of a cone, then we get a parabola. Here we see that if we slice off a part of a cone using a plane that's kind of tilted, so it's not flat, so we don't get a circle, but a tilted plane, that's how we get an ellipse. As with parabolas, ellipses tend to be strong shapes, and so you sometimes see them in bridges. You'll see textbook problems where you've got a bridge in the shape of a semi-elliptical arch, and it's again because of how the shape disperses weight. And as with parabolas, there are reflective properties of an ellipse. And here we see an individual who's in a tank of water. I swear they really do this. They'll put the individual at one focus, and then there's an agitator that will agitate the water at the other focus. The tank is in the shape of an ellipse. The reflective property that sends people into this situation is that if you agitate or you make waves at one focus of the ellipse, the waves will all bounce off of the edge and they will all collect at the other focus of the ellipse. So now you're wondering what poor individual will be sitting down here to be the recipient of all these agitating waves. They do this, folks, to break up kidney stones. So kidney stones are calcium deposits that are too large to pass. And rather than performing surgery, they'll stick the individual at one focus in this tank. They'll agitate the water at the other focus. The waves all collect here, and they break apart the kidney stones. I told that to a class one time. A student raised his hand and said, "They did that to me once. It feels really weird." Now, as a consequence of these reflective properties, we can also consider something called a whispering gallery. A whispering gallery is a room that has maybe not an exact shape of an ellipse, but the ceiling, as you can see in this picture here, the ceiling is kind of like the same shape as this bridge over here, right? It's an elliptical shape. And if you stand at one focus and you literally can whisper, a person standing at another focus, quite distant, maybe 100 or 200 feet away, will be able to hear you whispering. And this was actually used, there's one in our nation's capital. And it was when the American government was signing treaties with the Native Americans. And they would put the Native Americans at one focus of a whispering gallery in the shape of an ellipsoid is what it's called. And they would go stand at the other focus and eavesdrop while they were doing their negotiations. So there you have it, folks. Planets, bridges, kidney stones, and essentially stealing a country from the people who were here first.